very excited today. Thank you so much for having me. I'm always excited to talk about this fantastic mission that we have that is now on its way to Europa to explore the icy ocean world and tell us about Europa's potential habitability. Okay, let's see, slide. Okay, so I usually start off just to give a little bit of background about myself. I didn't have maybe the most straight path to becoming a planetary scientist, so I like to share that, especially when I talk to students and things, because I think a lot of us have this idea that we need to have a straight path, but it's not always what happens, and maybe you pick up some really nice skill sets along the way if you do other things along your way to your end goal. So I actually really thought I wanted to be an engineer when I was younger. I loved doing things, building things, playing with stuff, right? And I wanted to be an astronaut. So I have a picture of an astronaut there because that really was my end goal, like to go and explore, to be the explorer, right? Going out there. And I did get actually kind of close. I got one interview with the NASA astronauts, but I didn't quite make the selection. But along the way, I studied aerospace engineering. I got a master's in that, and I started working at NASA Goddard, where I was working on spacecraft, and I found it to be very interesting. But while I was actually finishing up my education, I became more and more interested in astrobiology. And at the time, there wasn't a lot of that really being studied. So I kind of kept that as an interest, but moved along and started working. But then I just decided to take the chance after I had been working at Goddard for a while and go back to school, and I studied geophysics, where I had an advisor who was an ocean ridge modeler and told me all about these hydrothermal vents. Here you can see in the middle, these black smokers, where back in the 70s, really fairly recently, we discovered these. And there are now theories, right, that these were the first places on Earth that life started. And so I was really intrigued about that. I also was lucky enough to get an internship while I was working my PhD and learned more about icy ocean worlds. Became really, really interested in those. Got a postdoc at Johns Hopkins Applied Physics Lab, where I am now, and have been fortunate enough to do some field work in Antarctica, doing lab experiments with DNA, extracting DNA, and trying to think about devices we might send to these icy ocean worlds to look for signs of life in the future. And so I've been at APL since 2013, so a little more than 10 years now, and I still just love it and love my job and feel very fortunate to get to work on all this really interesting stuff. So I start with a little bit of, talking about astrobiology. I think, what with this group, probably your focus is mostly interest, in astronomy, and that's definitely part of astrobiology. Like we like to use our telescopes to look out and look for, you can see in the upper right, plume activity maybe at these icy ocean worlds, telling us that these places might be active. Also providing a sample, maybe if we fly by and are able to do analyses on those samples that might tell us about what's in their oceans. And so astronomy, planetary science, astrobiology is just a highly interdisciplinary field, which is one thing that I just love about it, because you're just learning all the time. We work with astronomy folks, biologists, chemists, geologists, and physicists. It really takes people with all these various backgrounds to come together to explore these questions about, is life out there? How might it have started? How can we look for it? So it really takes everybody with all these different backgrounds, and it's just a really interesting field. And searching for life elsewhere in our universe is just really a major focus of NASA's strategic plan for exploring the solar system. And part of that is really, trying to understand, for at least as life as we know it, and then maybe trying to think about life as we don't know it, which is a little harder, but we try to do that too. But where do we look? Like, where are the places in our backyard and our solar system, but then maybe even beyond? Where do we look for these evidence of potential for life elsewhere? Next slide. So this has led me, at least, and many of my colleagues, as we learned more about the ocean worlds that are even just in our backyard, right? Just in our solar system. You can see many of them here. As we learned more about the fact that these worlds, these ice-covered worlds with oceans beneath, exist, we began to think about these as potential habitable environments, because it used to be for a long time, we thought all life needed sunlight, and that was how life got its energy and was able to survive. So we had a much more constrained region of our solar system that was in this, habitable zone due to the sun being able to have enough energy. But then we learned more about the potential for these ocean worlds, which I'll talk a little bit more about how we think, they're able to keep their oceans and where the energy might be coming from. But these are worlds in our backyard, even, that we have the ability to go and explore and look for, both establishing them as habitable environments and then also looking for, do they have life even today existing? So, starting just to go around a little bit here for our family photo of ocean worlds. We have Titan here, which is a very interesting world, has an atmosphere, but it's mostly methane and ethane. This world is at Saturn, out in the Saturn system. We have Triton here, which I have a little question mark at. We don't quite know for sure if it's an ocean world. This is a moon of Neptune, but we've seen potential geyser activity at Triton with past missions, and so it's an intriguing world that we would love to better characterize and understand. Ganymede, which of course, the European Space Agency has a mission on its way. JUICE, also on its way to Jupiter system to explore this ocean world. So we'll be learning a lot more about Ganymede in the future. And then Europa, which is the focus, of course, of the Europa Clipper mission, which I'll tell you more about. We're very excited about that because Europa's surface is young. It has these different colors, which, we know some about the compositions there, but we're going to be learning a lot more about what those are exactly. And then little Enceladus over here, very small moon, but when Cassini went by, it discovered this geyser activity at the south polar terrain, just spewing out icy particles from its ocean beneath. So it's really exciting. And many people hope to go back there and further explore. And then Mimas is another one, which there was even been a few papers recently talking about the potential for Mimas to have had an ocean, at least in its very recent past, if not maybe today as well. So these moons are all very exciting places, and they're all just in our backyard. But the question is, when we look out there, a lot of students we talk to, like, well, you look at them, and besides maybe Enceladus, which you can see the geyser activity, these are ice-covered ocean worlds. And so how do we even know that they have oceans in their interior? And we also want to understand, are those oceans or any pockets of water and places in the subsurface, are they habitable environments? And so I'll talk a little bit more about that and how we can use our understanding of their oceans and trying to understand their habitability. But just to set the setting a little bit more too for the Europa Clipper mission. So we're going out to Jupiter system. Europa is the second of the larger Galilean satellites of Jupiter. We do have some previous data from the Galileo spacecraft that flew by there in the late 90s to the early 2000s. But we're going to get much better data in terms of resolution with the Clipper mission, as well as just a much more additional information with various different instruments for sending. And then you can see Ganymede right next to it. We're very excited as well with the Clipper mission to also be out at this system at the same time as the JUICE mission, the ESA mission. And although ESA's mission will be focusing on Ganymede, they will be doing a couple flybys of Europa. And it's actually really exciting right now because our trajectories, there's one flyby that Clipper and JUICE fly by Europa about 4 hours apart from each other, which is just crazy to think about. And, we know that maybe the trajectories will have to get altered a little bit here and there between now and when we arrive. But it's just really exciting to think about having two spacecraft out in the system at the same time. So getting back to that question, how do we even know that these ocean worlds have oceans beneath? Because we just look at them and they have ice all over the surface. Well, the way we discovered Europa's ocean was from hints from the magnetometry data from the Galileo mission. So when the Galileo mission flew by Europa, Europa is small enough that we do think it has a core, but we don't think it has a liquid portion to its core because of the pressures that would be required to enable a liquid portion. So when the Galileo spacecraft flew by Europa, we were surprised in that the magnetometer measured an induced magnetic field at Europa. And so Jupiter has a very strong magnetic field. You can see in the bottom right in the GIF there that Jupiter has a strong magnetic field that passes through Europa, but it also has a periodic field, and it has two periodicities to that field. And so that actually is very interesting and enabling to us understanding the ocean properties at Europa. So to have measured this induced magnetic field at Europa, that meant that Europa had a magnetic material within its interior that was enabling this inducted magnetic field. And so that to us indicated there must be, we don't think it's this liquid metal, so we think it has to be a saltwater ocean. And that was just really exciting and unexpected. But that is where we are at right now with understanding Europa's ocean. And with the figure in the upper right, just to give you an idea, the fact that it has these two periodicities to the magnetic field, Jupiter's magnetic field, is enabling for it to help us constrain properties of the ocean. So the magnetic measurements that Clipper will make will be able to better constrain the ocean thickness and the conductivity of the ocean, and better help us in our understanding of this ocean's habitability. All right, so here's a picture then of what we think Europa's interior looks like. And so, Europa is about the size of our moon. We think it does have an iron core and then a rocky mantle, and then the ocean, the liquid water portion, and an ice shell over top. So you can see really relatively the ocean isn't much of that overall material of the moon itself. However, it is very deep, we think. We do think it's on the order of 100 to 120 kilometers deep. And another question that comes to people's minds, though, is like, Europa is way out there. I think the sun's energy levels is about 4% of what it is at Earth. So it's really, really not adding a lot of heat out there. And so how is this little moon able to keep its ocean over the billions of years that we think that its ocean's been in existence? And that comes in the fact that as Europa orbits Jupiter, it's sometimes a little closer and sometimes a little further away from Jupiter. And so it has a tidal forcing that's happening on the body. So it gets closer, it gets squeezed, it moves away, it relaxes, and it moves closer. And so that motion, as being depicted here on the right, causes frictional heating within the body. And so that actually focuses in both in the rocky mantle as well as in some in the ice shell. And that is shown here in the little bits of red that is showing up. But that heat is what we think has been enabling to Europa to keep its ocean over time. Okay, and so another really exciting thing that motion is enabling. So remember, the heat is somewhat concentrating in that rocky mantle. Well, similarly to how ocean ridges and the hot magma that's beneath the subsurface of our oceans can be enabling for hydrothermal activity. This is what we think could be potentially happening at Europa's seafloor. So these are places that just back in the 70s, we were exploring our ocean seafloors, and we came across these vents, putting all this chemistry, and this was like incredible, right? All of a sudden, we were in these oases where life was able to live and exist just living off the chemistry that was coming from these hydrothermal vents. So this is deep down in the ocean where the sunlight's just barely able to maybe be trickling through at extremely low levels. And the life that we found, the chemosynthetic life that's living, the smaller organisms can just live off just that chemistry from the hydrothermal vent. This is what really started to open up our thoughts to where in our own universe life could be existing. Because previously, like, we were concentrating a bit right on Mars and the fact that Mars had water on its surface in the past, and maybe it was a habitable environment in the past. But now we had these new worlds such as Europa, Enceladus, and Titan that were ice covered, but had this tidal motion, this tidal forcing that was keeping their portions of their ice shells liquid. And also potentially enabling this hydrothermal activity where that rock material interacting with the ocean and the water can allow the mixing of chemistry and allow these environments that may be supportive of life. So again, we don't really have a good constraint yet exactly on the thickness of the ocean versus its ice layer, but we know overall the thickness of that layer is about 120 kilometers thick. And if you take that amount, if you maybe estimate maybe 100 of that is actually liquid water, and again, reminding you, Europa is about the size of our moon, so not really large, but if you take all of that water and you compare it to the amount of water that's in all the oceans and rivers and lakes on the surface of the Earth, there's 2 times more water in Europa's ice, underneath its ice shell, than there is on Earth. And of course, that's just life needs water, and to have that much water is just really exciting and enabling. And we think this water has been around for billions of years. So of course, that's another constraint we don't really understand for life quite yet, is how long life needs to kind of get a hold and get established somewhere. But a few billion years, maybe that would be enough. And so it just is really exciting to think about that and the potential there for Europa's habitability. So when we look at our project here to try to go to Europa and establish whether Europa's ocean and maybe pockets within the ice shell are habitable environments, we really try to generally kind of constrain the idea of life. Okay, what does life need? Life needs water, or it needs a material that can be enabling for the mixing of chemistries. And as far as I know, and most of the chemists, and things, that water is really one of the best materials for allowing that mixing. We'll check one box. Europa's got lots of water. Okay, chemistry. The chemistry needs to be present. As far as we know, life really loves mixing of chemistries and being able to have your oxidants and reductants be able to be mixing. This is one thing that we're going to be further exploring with Europa Clipper, is understanding, are there pathways that may be enabling the radiation produced oxidants that are being formed at the surface to potentially mix with reductants that are potentially being produced by the hydrothermal activity at the seafloor. Are they able to make their way to one another and mix in these different environments? This would be something that life as we know it would really be promoted by. And then energy, what kind of chemical energy is produced by maybe that mixing of those materials or other chemistries and products that are available to life in these environments. These are very low energy environments. We don't expect that there would be a plethora and an overload of life in these environments, but we do think that there's the potential these environments have enough of what life needs. And so we'll be further constraining these 3 main aspects to understand whether Europa is a habitable environment. And so we really structured our mission around this. So the Europa Clipper mission, we launched in October. Yay, exciting. And our overarching science goal is to explore Europa and investigate its habitability. So we broke our objectives down into several main sort of categories. The first being the ice shell and ocean. We want to characterize that ice shell and any subsurface water, including understanding where they're similar across maybe a global perspective, or whether there's differences in certain regions of the ice shell. And also understanding, really importantly, that nature of any surface and ice and ocean exchange between those layers. We also want to understand Europa's composition. We want to understand if the habitability of Europa's ocean is dependent a lot, probably, on this composition and chemistry that may be present. We know there's salts on the surface, but we don't understand if those come from the subsurface, or those made through subsurface and surface interactions of materials. How are those compositions coming to be, and what are they exactly? The geology, we call it geology. Of course, this is ice geology as we are describing it. But we want to understand, we see all these really interesting features, just so many different types. You can see in the upper right picture, I'll have some other pictures as well, but there's cracks all over the surface. Some of them have this reddish material within them. Some of them have a sort of a shape to them that kind of indicates they're formed throughout Europa's tidal cycle. So it kind of has a crack opening potentially that's happening as the tidal motion is forcing that to be forming. Other features include chaos terrains, which look like jumbled pieces of ice that maybe had a more liquid layer beneath that allowed them to kind of toss and turn. So better understanding both, establishing what the geology is and then maybe how it was formed. And we're also trying to think forward, right? So these future missions, so the reconnaissance is something that we have in mind. We're going to be getting much higher resolution data. So In certain places, we'll be getting this extremely high resolution data at like 0.5 meter per pixel, where that information could be looked at later for both landing site safety as well as scientific interest, right? Trying to understand, is there maybe recent activity in this region that would make us also want to explore there? But for a future lander, for a future landed mission that could go and land on the surface and sample the near surface and subsurface for signs of life. And then also, very importantly, we're going to be looking for current and recent activity. So we've had a couple potential observations of plume activity by the Hubble Space Telescope. There's been other efforts to continue looking for activity. We haven't been able to confirm it yet. It's been kind of on the hairy edge of our signal to noise for these observations. But this will be something that the telescopes will continue to look at or look for as we journey to Europa. But once we get there, we have instruments and methods to also look for this activity. So here I just wanted to break out for a second and show you some really exciting. If you missed the launch, we ended up having a beautiful day for the launch. And after, I think was mentioned earlier, we had to weather a storm. Some people stayed in town. I actually got out with my family to make sure we were safe. But we got to see a beautiful launch then on October 14th of Europa Clipper on a Falcon Heavy. And so I thought I would just play. I'm going to skip kind of through a bit, like I'll skip forward so we don't take up the whole time with this. But I just want to let you enjoy the launch.
6, 5, 4, 3, 2, 1, ignition, and liftoff. Liftoff for Falcon Heavy with Europa Clipper, unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon, Europa.
Engine chamber pressures are nominal.
See that the chamber pressures are nominal as we hear. All 27 Merlin engines look great.
Rocket beginning to roll, putting down 5.1 million pounds of thrust. Is our camera team beside boosters? Once they do their job, they will be expended. If you're familiar with the Falcon Heavy, you know that they bring the boosters back on certain launches, but not on this one, because all of the performance is needed to push Europa Clipper into its proper orbit. In the second stage.
And that's where we need to get the engine start up.
Stand by for booster separation.
Booster engine cutoff. Side booster separation confirmed.
And there they go.
Okay, so that was really exciting. We're all so happy, right, as everything's continuing to go well. And then I just wanted to share with you as well that the separation. So another, of course, key moment is when the spacecraft, so here's Clipper, you can see our high gain antenna right here. These are the folded up solar arrays up near the top there. This is an instrument with one of the covers on right here. You can see some of our small places that we'll be using for maneuvering for our little thrusters on the spacecraft. But this is when it separates from the rocket.
Europa Clipper, separation confirmed.
And there you go. NASA's Europa Clipper probe, embarking on a long-awaited mission to study Jupiter's icy moon, Europa. And what a sight, Mick.
That is absolutely gorgeous, Gerald, to see Europa Clipper on its way. Successful deployment from stage 2. Falcon Heavy performed very well today. Teams behind us are clapping and enjoying. That is a beautiful picture.
Yeah, so really, really great. And I will share with you too some of the progress that we've been making with some of our deployments and things. So just to give you a brief overview of how we're going to get there. So we launched on October 14th here, which I've updated. Like you'll see the numbers are a little off because I threw in these numbers on top. As you know, we had a little bit of a delay to wait out the storm, but we launched on October 14th, and what we'll do first is do a flyby of Mars, which we'll do on March 1st. So just a reminder, most of our instruments still have their covers on and everything because they're designed to work out at Europa where it's extremely cold and they don't want to risk anything closer into the sun. So we will be doing two calibrations, one with the eThemis, the thermal imager, and one with our radar, our ice penetrating radar at Mars. So we will be getting a little data there that's going to help us with some of our calibrations. But then we do a swing back by Earth next December. And it's actually very close to my birthday, so I'm planning on having a flyby birthday party to wave at Europa as Clipper as she heads back out then to Jupiter. So overall, it's going to take us about 5.5 years from when we launch to when we arrive into the Jupiter system. So that's in April of 2030. But then also, just for awareness, it takes us another year or so to we're going really fast, and we have to kind of loop down and using a couple of the other moons to kind of help us pull in our trajectory to then start doing flybys of Europa. On the way, I mentioned this already, but we are going to be continuing to support observations, to be looking with Hubble and JWST for any signs of plume activity as we head out there. And if we see anything, maybe we can adjust our trajectory a bit if needed to fly by those regions. But we're really interested, right, because this is activity that could be similar to the activity that's happening at Enceladus, where we do believe that geyser activity is indicative of material coming from its ocean towards the surface. And so if we do make observations of plume activity at Europa, we'll be further trying to understand, is it similar to the Enceladus activity? How is it different? And just trying to learn as much as we can about what it can tell us. We do have in situ instruments that'll be flying through the environment at Europa. Even if there's not geyser activity, there could be material that's being kicked up from micrometeorite impacts and things that we'll be able to analyze and tell the compositions of. But here's a couple fun little GIFs and videos to show you. So on the left, I'm going to show you a video that's going to show you how we spiral in and then we start doing flybys of Europa. It's about a 3.5-year prime tour with about 49 flybys. And the colors here on the left are going to indicate our levels of radiation. So we are probably going to be limited mostly by the radiation levels that we encounter. So Jupiter has a very strong radiation environment. And that is actually partly why we chose to do flybys of Europa and not go into orbit at Europa. And it's basically because by orbiting Jupiter, we can make Europa our closest point of approach to Jupiter. And so we dip our toes in, we get our fantastic data at Europa as we do our flyby, and then we swing way out and get out of that strong radiation environment. And that enables us to have a longer mission lifetime and still achieve, as you can see on the right, this near global coverage of Europa. We will get global coverage of Europa, but at lower resolutions on the leading and trailing hemispheres. Sorry, I don't think I mentioned, in case you didn't know, Europa is tidally locked with Jupiter like our moon is, so it always has the same face facing Jupiter. So we also have a leading and trailing hemisphere that we call that. So that's, if you imagine, as Europa's traveling around Jupiter, it has a side that's facing in that travel direction, and that's the leading hemisphere, and the one that's on the back is the trailing. So that's where you kind of see more of a lack of these we call it a little bit of a spider web coverage there, but we are getting full coverage. It's just at lower resolutions from further away. Because at the right, you're seeing these closer flybys. And so this is giving you an idea of how close we're going to get. First of all, we get as close as 25 kilometers, shown in those regions are shown in red at the right. And then further out, we get the other flybys a little bit further out. But we do get extremely close to Europa for many of our flybys. And then the instruments that we have on board, we have 10 instruments. So of course, this is one of NASA's flagship level missions. So that's why we were able to have this high number of investigations on board. And we have it's about half and half between what we call remote sensing and then in situ investigations. And so the in situ ones are circled in gold and the remote sensing ones are in blue. And we have, I'll just quickly kind of talk through them here. So for the in situ ones, We have a mass spectrometer called mass specs. We have a dust analyzer, SUDA. We have a magnetometer, the Europa Clipper magnetometer. And we have a PIMS plasma instrument. And we have a gravity radioscience investigation. So that instrument is actually using our telemetry and commanding, communication signals to do the science that it will do. And then we have remote sensing instruments, including the Europa ultraviolet spectrograph. The ICE cameras is actually a suite of 2 cameras. There's a narrow angle and a wide angle camera. We have the MISE infrared spectrometer. eThemis is our thermal imager, and we have a Reason ice penetrating radar. And if you're familiar with the JUICE mission, they have a sister instrument, RIME and Reason. So RIME's on JUICE and Reason's on Clipper, and it's kind of fun, RIME and Reason. But those are both ice penetrating radars that will be active out there. And so these instruments are going to help us interrogate Europa. One thing is better understanding the surface. So as I mentioned, Europa is an extremely interesting surface. We think it's very geologically young, about 50 million years or so on average, which may not sound young, right? But geologically speaking, it's fairly young. We also we see a few craters, but not very many, which actually indicates to us that it's been resurfaced in the near past, which tells us that Europa's surface is active. We see many interesting ridge regions. Some of the ridges are kind of sinuous, kind of moving along. Others are straight, on a very straight path for extremely long distances. Chaos terrains. So this is the region I mentioned where it looks like these jumbled up ice blocks that have tossed and turned, maybe within a more fluidic matrix around them. And we also have these small little features we call lenticulae, or for our nickname for them are the freckles of Europa. But they're smaller features that we don't really understand how they form. Some of them are domes, so they're uplifted, and others are downwelling regions. And so these are really intriguing features as well. So our cameras, the suite of cameras, the ICE cameras, wide and narrow angles, are going to give us just much more information at much higher resolution than anything we've ever had before. So we do have the wide angle camera will give us information in color, as well as the narrow angle camera at its highest resolution of 0.5 meter per pixel. We're just going to get really down to the details here and really understand what is happening at Europa's surface in these regions that maybe from a further distance look fairly smooth, but then when you get up close, you find out just really interesting information about the surface there. So overall, just to tell you a little bit about what each of these investigations will do. So the MISE instrument will tell us a lot about the surface composition. It'll also be looking for evidence of endogenic activity. We'll be comparing observations, what we see with Clipper mission versus what the previous missions, Galileo and such, also observed, and see if there's been any changes between then and now. Europa UVS will be doing spectroscopic imaging, looking for activity off the limb of the moon. The thermal imager will be looking for heat signatures. So it's extremely, extremely cold, about 100 Kelvin on the surface of Europa on average. If any water is getting near the surface, it might be warming certain regions of Europa. So we'll be looking for that. The Reason ice penetrating radar will be able to tell us about any density contrast within the ice shell of Europa. It's also going to tell us, hopefully it'll be able to see that ice-ocean interface, so really help us better constrain the thickness of the ice shell. And of these instruments, we have, have a little family photo, as we like to say. We took some pictures of them as they were being integrated onto the spacecraft. And I have exciting news just as of this past Friday, and then as of yesterday, both the antennas for the VHF, we have 2 frequencies for the Reason antennas, very high frequency and high frequency, both deployed successfully. So, with each of these deployments, it's like a wipe of the brow, whew, and it's like really exciting that everything thus far is going very smoothly. But so that was a big news for this past week. And then our in situ investigations. So we have a dust and gas composition analyzer. So These instruments work extremely well as when we get our closest passes by the moon. So we're going to be collecting, as I mentioned, any material that may be coming out in a plume or geyser, or anything that's being kicked up off the surface. But both SUDA and mass specs can ingest these materials and tell us about the compositions. SUDA as well has a way of understanding where that material came from off the surface, so it can give us constraints potentially on which features the material is coming from, which will be very informative to us, especially if we see any geyser or current activity that we could relate maybe to certain feature types. And then we also have the plasma, a radiation monitor, and the magnetometer that are going to work very complementary with one another to measure the energetic field around Europa, the ions and electrons, and that'll help both constrain noise potentially, as the magnetometer tries to measure the magnetic field only, at Europa, but being in this other environment, it can have a way of removing that other information and being able to tell what's just coming from Europa. So these instruments will work very complementary and together to understand that environment. And we had another exciting deployment about a week ago. The magnetometer deployed, so it's an 8-meter long boom that had to sort of uncurl itself out. And they were able to, we have no cameras open right now, right, that can look and tell us if these deployments were completely successful, but they're able to take measurements as the sensors out at the end of the boom were deployed, and they were able to tell that the deployment was completely successful. So that was another really exciting moment recently. And then I just had a fun video. So this is now once we've gotten to Europa, and I'm going to take you through sort of a day in the life of a flyby. So just to orient you a little bit, every time you see a color kind of pop up taking an observation, that's related to the instruments that you can see listed over here. So one of the nice things that we have for our mission is that all the instruments that are going to be taking the remote sensing observations all point in the same direction together. So there's no like having to take turns and things. So we are able to take observations of the same place at the same time, all with multiple instruments. So it's really enabling for us understanding Europa's habitability and getting all that information. One of the other interesting things to point out to you is that our radar antennas are attached to our solar panels. So of course, most of the time you have your solar panels pointed towards the sun, but as we get really close to Europa, you'll notice that the solar panels rotate to enable the radar to face Europa. You'll just saw a spacecraft scan happen, but most of these observations are happening together. Different instruments turn on as we get closer and closer. Certain ones need to be much closer than others to take their observations. So you get full field observations, and then I think, yep, right now is when the solar panels rotate to turn the radar antennas facing Europa. And then as we get really close, it happens really fast, but we take data all the way on the way in, closest approach, and then we turn and we continue to take data on the way back out. And so this is our flyby. It's about 2 hours on the prior side to the 2 hours on the far side to when we get most of our data, with then a few of the instruments able to take data from further away. And then it's about 2 weeks at certain times, and then about 3 weeks in between each flyby. So we have time to downlink and assess and prepare for the next flyby. Okay. Also, just wanted to show you some pictures that were taken during spacecraft integration and test. So as I mentioned, Europa is in this very harsh radiation environment at Jupiter. So there's a large vault that was constructed to put most of our electronics into. And so that's what you're seeing here at the left. This is our full up spacecraft. So this is the, everything's being attached here. This is what's holding all of our fuel and everything. You can see the people working. These white sheets here are sort of templates for the thermal blankets that were being prepared to be attached there. We had colleagues or partners in Europe and Airbus that ones that constructed the solar panels for us. I believe they're the same company that made the ones for JUICE as well. but here they are, testing them out and doing their checks on them. And then also at the right, I have a picture of the high gain antenna. It's about 1.8 meters in diameter. We also did some efforts to reach out to the public. We really tried to reach out to the world as well as to other like fields, I guess you could say. So we had a collaboration with the U.S. poet laureate Ada Limon, who wrote a poem for our mission. So really trying to pull in, just various aspects of the world, right? Of trying to reach the arts as well and bring them in. People were able to sign up to send their name to Europa. So that actually, all the names were actually micro etched into a plate that was attached to the spacecraft and was sent with the spacecraft on its way. And here's a couple links. Pretty much if you do a search for Europa Clipper and NASA, you'll find the main page, europa.nasa.gov. There's also a really fun site that you could go to. It's called Eyes on the Solar System. I think if you just search for that, you can get to this link. But it's actually a really nice way of seeing all the spacecraft that are currently out in the solar system, going to places. JUICE is on there and Clipper's on there, and you can pick different views on the bottom left corner to kind of like the one I like to pick is the sun view, where you're overlooking sort of the plane of the solar system, and so it's a little bit easier to kind of see where things are. But you can follow along as we make our way to Jupiter. And I just then wanted to continue. I know I've been going for a while, and I hope everyone's still awake and interested, but I'm going to just give you a little bit of what I envision that we're going to hopefully be doing as a follow-on. What we're going to Europa, we're going to Ganymede with these fantastic missions, but what do we hope for in the future, and what is NASA thinking about sending? So I've been working with some groups thinking about this strategy for ocean world exploration. The Mars community for a long time had this strategy of we're going to go, we're going to do flybys, we're going to land, we're going to rove, we're going to explore and look for signs of life. Well, ocean worlds kind of need that, and we do generally have this idea of we're doing these flyby missions now, right? We did Cassini in the past, and Galileo, and then we have JUICE and Clipper going to do the flybys, more flybys. And so hopefully the next thing that'll happen, right, is that we send more missions back to land. So this is a concept for Enceladus, landing on Enceladus, both collecting plume material as it falls down into your funnel, looking for signs of life, as well as a Europa lander maybe that it has the special tools to dig into this really cryogenically hard ice and look for signs of life. And then, we want to rove, but roving on these ocean worlds might look, maybe a little bit different than what we've done traditionally on Mars. We have the Dragonfly mission that, the thick enough atmosphere on Titan is enabling for a quadcopter to go and fly around on Titan. Potentially in the future, we will melt our way through Europa's ice shell and get to its ocean and swim around in its ocean and look for signs of life. These might sound a little far out there, right? But we really have to think about these concepts, and they are technologies that we have that we can build upon, that we use for terrestrial exploration, that just need a little bit of forward thinking and development to make it possible. So I've been involved with Europa Lander mission concept, where we really tried to think a lot about if we were going to look for signs of life, like what do we need landing on a potentially hazardous, but very scientifically interesting, landing sites. We have to be able to sample, bringing in enough sample for each of our instruments that's going to be maybe taking apart the sample and looking for these biomolecules that might be present. And if we see them, what can we learn about the life there? Has it been degraded from that harsh radiation that has been sitting out on the surface? And also doing geophysical and visual observations to support that information of why, if we find life there, like why is it there? Or if it's not, if we don't find it, why didn't we see it? And then there's been lots of development on the engineering side for how to safely land, drawing from previous Mars concepts with the sky crane, right, to get you in a really precise location where it's a safe area, and then to softly touch down on the surface without any atmosphere to help you out. So there's lots of information out there about Europa Lander if you're interested in learning more about that mission concept. There's also another study that was done particularly for Enceladus, So an Enceladus Orbilander concept was formed and led by Shannon McKenzie here at APL, where the idea was that you could go and sample both the plume material while you're in orbit, then you can land and further collect sample as well as digging into the surface and really doing very similar kind of studies for looking for signs of life. Like we really know that these ocean worlds are very likely habitable environments, but do they have life there today? And that's the question we want to answer. And then in the future, you know, maybe it's tantalizing data that we get from the surface, but really we know these worlds have these vast oceans beneath their ice shell. So how fantastic would it be to actually be able to get down into that ocean and look for signs of life in the ocean? Because maybe the material hasn't been able and the organisms haven't been able to make their way to the surface. So we need to answer this question, potentially get down to that ocean. So there's been studies thinking about how you actually would make a cryobot that could melt its way through. And then also the technologies needed to support that, right? So if you're making your way through the ice shell, you're melting your way through, that water is refreezing around maybe a fiber optic tether that you have behind you that is your lifeline, right, to the surface where you're going to send your commands and data to and from the Earth. You have to be able to know and have confidence that that's going to survive, right, for a multi-year mission, probably for getting through this ice shell. And so I've been part of this Signals Through the Ice team thinking about this. And it's been really incredible to find partners who have these apparatuses. Our one partner at Lamont Dougherty in New York, we're able to freeze portions of these fiber optic tethers across blocks of ice. So they're held across here, they're frozen in. And then when they put on this rig, which is kept at these cryogenically cold temperatures, you can put force on the center block and do shifting to simulate shear motion. So we see these faults and things on Europa's surface. If your tether just happened to cross one of these faults, is it going to survive, right, for a couple years as Europa's tidally moving as it goes around Jupiter? And so we've applied stress and simulated this, and the tether actually is fairly robust, and we're very encouraged by the results, but we're further exploring these types of communication devices for sending these someday to Europa. And then, of course, we have this crazy exciting mission, Dragonfly to Titan. I mean, I would be remiss, APL would disown me if I didn't actually at least mention this mission, right? It's just a fantastically exciting mission to Titan, the ocean world at Saturn, where, you know, it has this really interesting, probably kind of early Earth similar type of environment where we don't necessarily think there's life here today, but this is a very, an environment that might have kind of like this building blocks of life present. And so it has a very interesting photochemical atmosphere. It's organically rich surface and ice crust and a subsurface ocean. And so the question here is, what complex organics are formed in the atmosphere? Have they been, and how have they been chemically and physically modified on the surface? And do they interact with that subsurface ocean? And so Dragonfly is going to go and explore this really interesting and intriguing world, looking for these building blocks of life, and if it has these key ingredients that life would need. And so I mentioned this, it's going to study the prebiotic chemistry, habitable environments, and look for biosignatures. And then here's a fun video showing you how taking advantage, right, of Titan's atmosphere to slow itself down with a parachute first, but then detaching and going on its own power, using these terrain relative navigation systems that are enabling to find a safe landing site. And it has a nuclear power source. This is the tail kind of the lander here is the RTG that's powering the system. But then landing, taking data, flying around, find another safe landing spot to go to next, and then going there. So really fantastic and exciting mission to Titan. It's planned to launch in 2038. And then just quickly, I'm going to mention, we're also, of course, you know, when we talk about looking for biosignatures, I mean, that's a whole nother, you know, can of worms in itself, right? So How do you deal with, like, we know these environments are challenging, they're salty, they have challenging chemistries, there's high radiation. We have to send our instruments in very small packages. They can't take a lot of mass or power or volume space. So how do you design these instruments to fit in these small packages, but also do this really complex chemistry and looking for these biomolecules that might be present? So we're working a lot with microfluidic devices, trying to think about sample preparation. If it's a very salty environment, that can be bad for your mass spectrometer down the line. So you want to clean it up first, pull out the amino acids if they're there and get rid of all the other stuff that you don't want to, well, somebody probably wants to look at it. Give that to the other instrument, but then send the purified amino acids down to your mass spectrometer. And again, astrobiology, you're working with chemists and engineers and biologists and planetary scientists. It's just a very fun team because you're always having to use different parts of your brain to try to get at this complex question. We're also trying to think about more complex biosignatures. What if life has evolved to the point where it can pass down its genetic information from biomolecule or organism to organism? And these are low energy environments. So we first concentrate the sample so we can get that higher signal to noise. We break open any spores or cell walls that are present and release that biosignature and then purify it again, right? Removing salts and other inhibitors to be able to make our detections. But there's devices out there, right? I mean, right now there's nanopore devices that are used for human and other like extreme environment exploration where you can attach this nanopore sequencer to your laptop, insert the sample, and it can sequence for you and tell you what organisms are present. So taking these devices that are already sort of small form factor, but then making them more robust for spaceflight is part of what we think about as well. And then the other aspect, of course, always to think about is planetary protection. So when you hear that, you might think about the samples that people want to bring back. We don't want to bring anything dangerous back to Earth, but we also don't want to take anything Earth centric, right? Earth origin to another world, implant it there, and then maybe someday later have a hard time telling if what we found was something that we had brought with us or had sort of contaminated that planet with. And so there's a lot of effort too to think about making sure your spacecraft is clean, but also you're not bringing anything with you. And if you've done some interrogation of biosignatures, that you're able to clean up afterwards, that you don't leave anything behind. So these are all things that we've been thinking about. And so that is where I'm going to finish up here. I'm going to say, onward to Europa and Ocean Worlds is a very exciting time with these two fantastic missions on their way to the Jupiter system to explore Europa and Ganymede. And Dragonfly is coming. 2038 is the arrival. Sorry, 2028. I might have misspoken earlier. 2028 is the launch day for arrival in the 2030s. And hopefully in the future, we'll have missions that will go back and land on these worlds, interrogate the near subsurface using instruments that we're working on to look for biosignatures. And then potentially in the future, we go to their oceans and we further explore these exciting worlds. And so with that, I'll finish up and just say thank you and hopefully have left time for questions.